Okay, so like I said last time, we talked about in section 5.7, we talked about how we could use linear algebra, our understanding of linear algebra, to help us solve linear systems of differential equations. And essentially, the solution to a linear system of differential equations is a combination of eigenfunctions for a particular matrix A that corresponds to the system of differential equations. And we looked at real eigenvalues and real eigenvectors. We looked at and now we're going to look at complex eigenvalues and eigenvectors and look at a solution involving a system involving those. So let me give you a moment to copy this example down. Okay, so all right, so let's see here. I want to, one moment. Okay, so we have here a solution to a differential equation that can be broken down into a vector that we call x sub real of t plus an imaginary number I times another vector that we call x sub im of t, x sub imaginary of t. Now, what's important to understand is that these vectors, x sub real of t and x sub im of t, the components of those vectors are real functions of t, real functions of t. But what makes this vector x of t, this solution vector, complex is the fact that you have this imaginary I here as the coefficient of one of that second x sub I vector. So that's why we call then, if the vector x of t has an imaginary I in it, we can split it up and write it as you see here in this form, and we call it a complex valued solution of a linear system of differential equations. And we're going to suppose now that this is a complex valued solution vector of a linear system of differential equations. If that's the case, then in fact, it turns out that the vector x sub real of t and the vector x sub I of t are also both solutions to the system of differential equations. And they're real solutions because the components of x sub real of t and the components of x sub I of t, and that's the notation I like to use. Those components are going to be real functions of t. Okay. All right. So I want to prove this to you. May I go to the next page? All right. Very good. Thank you, Namath. Thank you, Benjamin. All right, we'll go to the next page here. And this is how we're going to prove that result. So I'm going to take the derivative of this solution vector x of t. And x of t, remember, can be written as a vector x real of t plus an imaginary I times a vector x imaginary of t. X, or I call it xi of t. I mean, we can write the vector in that form. Now, we have to note that by hypothesis, hold on here. By hypothesis in this problem, we're supposing that this vector is a solution to the differential equation. Well, that means then that dx of t would have to equal a times that vector, dx of t, the derivative of the vector x of t with respect to time would have to equal a times x of t. And what is x of t? It's x sub real of t plus I times x sub I of t. And we can say this, that dx, the derivative of the vector x with respect to time equals a times that vector x right here, because we're by hypothesis told that the vector x is the solution to the linear system of differential equations. Now we're going to make use of this. We're going to make use of this fact later. Okay, but let's continue forward. So, okay, well now what I want to do is I want to take the derivative of the sum of two vectors. Well, the derivative of the sum of two vectors is the derivative of the first vector plus the derivative of the second vector. Okay. Now the second vector has a constant I. It's an imaginary constant, but it's in front of the vector, and we can factor that I out. Okay. So are we okay up to this stage here? Let's make sure. All right, Natalie's good. Okay, all right. Well, now, again, okay, we have to recognize that this, the sum, that sum is equal to this sum here. And where's that sum come from? That comes from up here. A times x real of t, if I distribute the A, if I distribute it, that matrix A, across both terms, that's going to get me what we have here. So certainly these two are equal. And if those two are equal, then the derivative of the x real of t vector would have to equal A times x real of t. Similarly, the derivative of x im of t would have to equal A times x im of t. It has to. There's no other choice. It's like if you say, you know, if you say A plus BI, if you say that equals 2 plus 3i, okay, this is like an analogy here. If A plus BI equals 2 plus 3i, what's that tell you about A? What does A have to equal? And what's that tell you about B? What does B have to equal? So here, if A plus BI equals 2 plus 3i, what does A have to equal, class? Who can chat it out? That's right, Eleanor. A equals 2 and B equals 3. Well, I'm doing a similar thing here. The derivative of x real of t has to equal A times x real of t. And the derivative of x im of t has to equal A times x im of t. And that gets us then these two results. And therefore, x real of t and x im of t are also solutions. They are also solutions to the linear system of differential equations. And they're real solutions. These are real solutions. And that's what we want, because the trajectory in the xy plane, okay, even though that based on the matrix A, you might have complex eigenvalues and complex eigenvectors. If you're going to describe the trajectory in the real xy plane, you need to have real vectors, real functions of time to describe that trajectory. Okay, let me know if you have any questions. All right, well, then if you're good, class, we can move to an example. All right, may I move to the next page? All right, Eleanor's ready. Good. Okay, name us good. Okay. Well, all right, here's an example. Here's an example. And actually, this example corresponds to example 3 in the textbook. Now, well, let me give you a moment to copy the example down, and then I'll talk a little more about this. Okay, so, all right. One moment here. Okay, so remember, let me see, I'm just debating whether maybe I'll try to use my stylus here for this. Hold on, we'll see here. So you've learned that a general solution to a linear system of differential equations can be written as a linear combination of the eigenfunctions. This is now, of course, we're doing this, what I'm writing up here is for when we have two differential equations. Okay, two differential equations means you're going to have two eigenfunctions. How many recall doing this a lot in the homework? How many recall that? Sure, Ariana remembers it. And in the homework that you had for section 5.7, the eigenvalues, the lambda 1 and lambda 2 were real, and the eigenvectors were real eigenvectors. Well, the same result is true when we have complex eigenvalues and complex eigenvectors. The same result is true. And if we were to put in complex eigenvalues and complex eigenvectors, we would just have a complex solution. But in this scenario here, for our example, this particle is moving in a planar force field, a two-dimensional force field, and the position vector and differential equation, x prime equals ax, that the linear system of differential equations satisfy these conditions. So we're going to have to get a solution x that describes the trajectory of the particle in terms of real functions, because we're not working in a complex space. We're working in real two-dimensional space. And I want to mention something else also regarding this. If we go to example 3 in the book, let me just go to example 3 real quick. Okay, so this problem we're doing goes with example 3, and the differential equations are actually given here by this matrix equation, where you're on the left, you have the derivatives of current and voltage, and it equals then that 2 by 2 matrix times the current and voltage vector on the right. I sub L is the current passing through an inductor L, and V sub V is the voltage drop across the capacitor. Okay, and so of course these equations would relate to Kirchhoff's law. How many have heard of Kirchhoff's law, maybe in physics? Okay, Lewis has, Justin has, and Eleni has. And how many have seen maybe these kind of equations in maybe a class they've taken? These has anybody seen that formally? Okay, Justin's seen it in electronics. Okay, all right. So now you don't need to know electronics or electrical engineering or physics. I mean, to do this, I mean they give you the setup, and then they tell you but below what your resistance is. Okay, resistance 1, resistance 2, capacitance, inductance, and you're finding formulas for the initial current through the inductor. Well, you're finding formulas for the current passing through the inductor, that's I sub L, and V sub C is the voltage drop across the capacitor. Okay, and they give you values. So what you would do is you would substitute the values in that 2 by 2 matrix there. So like for instance, like for the first entry here, maybe I can hold on here. For this entry here, because I'm thinking about the homework. Okay, when you see this, for the first entry there, hold on. Did it go blank on us? Hold on, let me get it back. Hold on. Okay, good. So for the first entry there, negative R2 over L, well, R sub 2 is 0.8 ohms, and L is 0.4 henries. So 0.8 divided by 0.2 is 2, and that's how, for instance, you get the -2 here. Okay, and you can find the rest of the entries similarly. Okay, so it's a doable problem, and I think it's important that some of you have seen this already, and it's good to see it how we're applying it to linear algebra. Any questions on that? Okay, and I see figure 4 circuit diagram on the left. All right, well, let's go back now to working through this problem. Hold on here. Okay, so, all right. Now, in this case, I'm talking about, well, we think of it like a particle moving in a force field, and what do we have to find, class? What do we have to find here to solve the system of linear differential equations, right? This is the system, or the linear system of differential equations. X prime, the vector x prime equals a times x. So what do we have to solve for here? Well, what do we have to find? What do we have to find on the homework that was due today? What did you have to find? I'll give you a hint. Begins with an E. Okay, good. Eigenvectors and eigenvalues. Good, good, good. So we're going to do that. So, okay, it can be shown that the matrix A has the corresponding eigenvalues and eigenvectors. Let me give you a moment to copy that down there. Okay, and what I want to do, I want to take you into MATLAB just briefly to show you how how MATLAB gets these. So we're basically up to here now. Let's go into MATLAB for a moment. So let's go into MATLAB. Okay, so what I did was, class, I hit new. Yeah, I clicked on new here. Hold on. I clicked on new, and that opened up the script editor, and then I put in this script. So I put in the matrix A, and I'm going to find the eigenvalues and eigenvectors. Eigenvectors will be stored in the matrix V, and eigenvalues will be stored in the matrix D. So I'm going to copy that. Okay. And actually, maybe before even I do that, hold on, let me do the command here, clear vars. I like to make sure my variables are cleared out, any old variables, so they don't interfere with my current code. I paste it in, I hit enter, and now I have my eigenvalues along the diagonal of matrix D, -2 plus or minus 5i. And then the eigenvectors, corresponding eigenvectors, are -1i over 2 and 1, and then 1i over 2 and 1, those components. Now, of course, I don't like fractions. If I can help it, I like to try to avoid fractions. So what I'm going to do for those two eigenvectors, instead of using -1/2i and 1, I'll multiply by 2 and use -i and 2. And instead of 1/2i and 1, I'll have I and 2. I'll multiply. Any multiple of an eigenvector is automatically an eigenvector. Okay, are there any questions on that? Okay, well then let's get back to the problem at hand here. Okay, so we found our eigenvalues and eigenfunctions. Now, of course, both eigenfunctions are solutions to the linear system of differential equations. Okay, I mean, a linear combination of the eigenfunctions is a solution to the linear system of differential equations. So one eigenfunction would also be a solution. And what I do is I focus on the first eigenvalue and the corresponding eigenfunction, corresponding eigenvector. And I write down that eigenfunction right here. x1 of t, which is one of the eigenfunctions, is equal to e to the negative lambda t times the eigenvector. That's therefore e to the quantity -2 plus 5i t, -2 plus 5i times t times the eigenvector I2. Now what we can do, what the amazing thing here is that we, based on this one complex eigenfunction, we can get the real solution for this linear system of differential equations. It's absolutely amazing, and let me show you how this works. So what I do is I take, well, I mean this here, hold on, this here is equal to e to the -2t plus 5it if I distribute the t. But then that equals e to the negative 2t times e to the 5it. And that's how I get this here. Now, what we're going to do is this e to the 5it. Well, how many of you have heard of Euler's formula, where e to the I theta equals cosine theta plus I times the sine of theta? It can be proven using Maclaurin's series quite easily. But how many have seen that maybe in another class? Euler's formula. Okay, Justin's seen it. He doesn't know where, doesn't know which class, but he's seen it. Okay, has anybody else seen that? Benjamin's seen it in signal analysis. Okay. Okay. Well, and we're gonna see it here as well. We're gonna see it here as well. Let me just hold on one moment. Okay, hold on, class. Okay, good, good. Just wanted to turn off my email there. I don't want any distractions. So it turns out that e to the 5it by Euler's method equals cosine 5t plus I times the sine of 5t. And what we can do is we can distribute, okay, let me just clear this a little bit. We can take the cosine of 5t plus I times the sine of 5t. That's a complex function, but we're going to multiply it through the vector with components I and 2. And don't forget, we do have an e to the negative 2t here as well. So if we do that, well, if you take e to the negative 2t and distribute it into this complex function, you'll get e to the negative 2t cosine of 5t plus I e to the negative 2t times sine of 5t. That's what you're going to get here. And then, you know, you get that. And then, of course, you're going to multiply that function, complex function, by both components here. So let me clarify again what we're doing here. So I'm taking e to the negative 2t and I'm multiplying it by the cosine of 5 of t and by I times the sine of 5 of t. And when I do that, that's going to get me this complex function here. Okay, but then I'm going to take that complex function and multiply it, okay, by the vector I. Okay, similarly, I'm going to take that same complex function and multiply it by the component 2. So we took that complex function and multiplied it by component I and component 2, and that gets us here. Are there any questions on that? This is something you have to do out by hand, by the way. This is not something that, this is something like on your next exam, for instance, I would want you to work out by hand this process. Now what we're going to do is we're going to distribute the I, that component I, into that complex function and distribute the 2 into that complex function. and this is going to get us down to here. And the goal here eventually, well, we're not too far away. The goal is to ascertain real solutions to the linear system of differential equations. Please let me know if you have any questions. Okay, so again here, our complex eigenfunction, x1 of t, is now equal to this complex vector. Can we split the complex vector up? Can we write this complex vector here as, I mean, our goal should be to take, well, let me just, hold on here. Hold on. Our goal should be to take this vector and express it as x real of t plus I times x im of t. Okay, so can I do that? Can I take this vector and split it, you think? With one vector that's just a vector, one vector plus imaginary I times another vector. Can we do that? Is that doable? Can I take this vector here and write it in this form here on the left? Absolutely. Absolutely we can. That's right, Justin. Okay, so let me show you what that would be. Are there any questions so far? All right. This is what x1 of t would be. We can rewrite that vector that you just saw. We can rewrite it this way. All right, please let me know if you have any questions. All right, so look at what we have now. look at what we have. We have this x real of t vector, and we have this xim of t vector. And we learned that both of those vectors, I mean, both of those vectors are solutions, real solutions, to the linear system of differential equations. And therefore, the general real solution to the linear system of differential equations is going to be given as this vector here. X of t will equal c1 times the vector negative sine of 5t, 2 cosine of, I'm sorry, let me say that again. The real solution vector is going to equal c1 times the vector with components negative sine of 5t, 2 cosine of 5t, times e to the negative 2t, plus c2 times the vector. I want to say this again. I'm sorry. I'm not saying this the way I want to say it. The real solution, x of t, to the linear system of differential equations is equal to c1 times the vector with components negative sine of 5t, cosine of 5t, times e to the negative 2t, plus c2 times the vector with components cosine of 5t, 2 and 2 sine of 5t, times e to the negative 2t. We have the real solution. So a linear combination of the x sub real vector and x sub line vector would be a general solution. And it is a real general solution to the linear system of differential equations. We proved that, and you know, we proved that this this is actually this is okay. So therefore now we want to solve. Well, are there any questions up to here? And you see this a lot, you know, in math. Essentially, these two vectors here, this vector and this vector, form essentially what's called a fundamental set of solutions for the linear system of differential equations. Fundamental set, it comes up a lot. It comes up in differential equations, for instance. How many have heard of a fundamental set of solutions before, maybe in another class? Well, if you, hey, you know, this is a first time for everything, right? But now what we want to do is we want to actually now apply the initial conditions. So x of 0 is equal to 3, 3. So what we're going to do is hold on here. For our solution here, we're going to substitute in wherever we see a t, we're going to let t equal 0. And by doing so, well, you know, this here is a 0 because the negative sign of 5 times 0 is negative sign of 0. That's 0. This value is a 2 because 2 times the cosine of 0 is 2 times 1. That's 2. And similarly, you'll get 1 and 0 over here. And so this allows you then to solve for C1 and C2. Okay, are there any questions before we move to the next page? Okay. Well, we can then put in the C1 equals 1.5 and C2 equals 3. We can put those values in, and we can write the general solution to the initial value problem this way as well. If you factor out e to the negative t, you can write the solution this way. So I'm showing you different forms of the solution. And based on this, we can sketch a trajectory of the particle. Now, this trajectory below comes from figure 5. Okay, but I'll explain how you'll notice. Well, so for our initial condition, which is x sub 0 equals 3, 3, the solution is spiraling inward to the origin. Okay, spiraling inward to the origin. Why would that be the case based on the solution here to our initial value problem? Why would the solution spiral? Well, what's causing the spiraling in figure 5 below? What's causing that spiraling, class? Why is the solution spiraling into the origin? Based on this here. Well, you know, Haley, the thing is, though, there's no complex eigenvalues in this solution x of t, although we needed the complex eigenvalues to get there. So, yeah, and the sine and the cosine. That's right, Hung. That's right. So sines and cosines, we know there's oscillatory behavior, right, with sines and cosines. And in terms of coordinates, then, because remember, you have two coordinates here in your solution. You have two coordinates. You have this coordinate, e to the negative 2t times that function there, and then you have this other coordinate, right? And so spiraling is caused by the sines and cosines. But why now? Why is the solution spiraling into the origin? Why is it not spiraling away from the origin? Okay, Hung says because of this negative 2t. Okay, the negative 2t, that's right. What does e to the negative 2t approach? What does that approach as t goes to infinity? What does e to the negative 2t approach as t goes to infinity? I think you're too scared to answer, right? Does e to the negative 2t exponentially increase or decrease? Based on the fact that the exponent's negative, e to the negative 2t should exponentially what? Increase or decrease? It decreases and it goes to 0. It goes to 0. So this entire vector here is going to approach the origin. As t goes to infinity. As t approaches infinity. So it's like an attractor, right? The origin's an attractor. Are there any questions on that? Please let me know if you're uncomfortable. Justin says this comes up in quantum mechanics. Okay, okay. Oh, very good, very good. Yeah, I mean, this is, you know, and what's beautiful here is how many remember seeing this kind of solution perhaps in differential equations? If they took differential equations, you would see a solution that might look like this, based on complex eigenvalues and eigenvectors. Benjamin remembers it. And at that time, because there's not enough time in the course to talk about the theory, you just kind of accepted it on faith. But now you know why it's true. Now you know why that's true. And if you're going to take differential equations, when you encounter this kind of material, you'll know why it's true. Okay, all right. Well, now, so you'll notice that the solution spirals inward, and it does it in a counterclockwise fashion. So why is that? I mean, you know, why doesn't it spiral? Why doesn't the solution, the trajectory, why doesn't it spiral into the origin in a clockwise direction? Well, one way, now this is not in the book. I don't see this talked about in the book, but remember, if you go from one point to any other point, you can construct an approximate right triangle and have a delta x1 and a delta x2. Well, delta x1, delta x2 over delta x1 is like dx2 over dx1, okay? So dx1, the derivative dx1 dt, when x1 equals and x2 equals 3, based on the differential equation for dx d1 dt, if I go back here, you know, dx d1 dt is going to equal negative 2x1 minus 2.5 x2. All right, that's what dx d1 dt is. So therefore, when x1 equals 3 and x2 equals 3, dx d1 dt is going to equal negative 2 times 3 minus 2.5 times 3, which equals negative 13.5. Similarly, dx d2 dt, okay, based on the second differential equation is dx d2 dt equals, the second differential equation is dx2 dt equals 10x1 minus 2x2. Okay, well, so then here is at 3, 3, dx2 dt is 10 times 3 minus 2 times 3, and that's 24. So what's happening is based on well, we have these derivatives, and then the delta x2 divided by delta x1 is approximately dx2 over dx1, and that can be written as the ratio of these derivatives, dx2 dt over dx1 dt, and that's going to equal negative 24 over negative 13.5. So think about rise over run. Rise over run. You can never get away from it. Rise over run. delta x2 here is a rise. Delta x2 is a rise. Well, according to our information, that rise is positive. And then delta x1 here is a run. And according to our information, that run is a negative value, negative 13.5. So that means then that the particle has to be moving in the counterclockwise direction. Okay, and then it just commits to that, and it keeps going until it reaches the origin. Okay. How many say, wow, that's a lot of calculus there? That's a lot of calculus. How many remember that kind of calculus from Calculus 2? Sure, Hung remembers it. And Benjamin does. Catherine, yeah. So, are there any questions? Any questions on this problem? How many think this is pretty cool? Pretty cool. Lewis likes it. Thank you, Lewis. Natalie likes it. Benjamin likes it. Thank you, Natalie. Thank you, Benjamin. I mean, Hung likes it. Yeah, you just learned Chapter 8 in differential equations at Montgomery College. You understand now why the solutions are the way they are. All right, let me stop the recording.